We want to do various calculus techniques with sequences because they come in very handy for determining all kinds of stuff that we will be working with in the future. First thing I want to look at here in terms of calculus is I want to take the limit of a sequence. So if the terms of a sequence an approach a unique number L as n increases, then we say the limit as n goes to infinity of an equals L. This should look familiar. We would have done this before, like limit as x goes to infinity of f of x equals L. It's the same idea. We say this limit exists, and the sequence is said to converge. So the sequence converges to L. Now, if the terms of the sequence do not approach a single number as n increases, and this should be one word, looks like I got a space in there, sorry about that, then the sequence has no limit, and the sequence diverges. Now, divergence here does not necessarily mean it goes to infinity. So it may or may not go to infinity. Commonly in the past, when we talked about divergence, as it was related to integrals, something that diverged we typically thought of as blowing up on us has an infinite amount of area. But that's not necessarily true. It's simply saying that the area is not finite, it's not determinable. And that's what this is saying here. A sequence could diverge but not necessarily go to infinity. And matter of fact, I'll show you an example right now. Let's take a look at an, and I want to know if this sequence will converge or diverge. And I'm not going to work with a limit on this one. I'm just going to start writing out some terms. So a1 equals 1 plus negative 1 to the first. That's 1 minus 1. That's 0. a2 equals 1 plus negative 1 squared. That's 1 plus 1. That's 2. a3 equals 1 plus negative 1 cubed. That's negative 1. So 1 minus 1 is 0. a4 equals 1 plus negative 1 to the fourth. So that's just 1. 1 plus 1 is 2. So you can see what's going on here. If I were to graph this, 1, 2, 3, 4, 5. That's good enough. At 1, I'm at 0. 1, 2. And at 2, I'm at 2. At 3, I'm at 0. At 4, I'm at 2. So I get this thing going up and back down, and then back up. And you know the next one's going to be going back down. And this just continues on to infinity. It never levels off. Therefore, it's divergent. It didn't shoot off into infinity, but it never settled down. It never converged to a single value L. So an is divergent. Now here, let's take a look at an equals 3 minus 1 over 2 to the n. In this example, I can start writing out a couple of terms, and a1 will equal 3 minus 1 over 2 to the first. That's 5 halves. a2 equals 3 minus 1 over 2 squared. That's 3 minus 1/4. That is what? 12 minus 1 is 11/4. a3 equals 3 minus 1 over 2 cubed. That's 3 minus an eighth. That's going to be 23/8. a4 equals 3 minus 1 over 2 to the fourth. That's 3 minus 1 over 16, which is going to give me 47/16. And I think we can see what's going on here. As n gets bigger and bigger and bigger, I'm actually subtracting off a smaller and smaller piece. So eventually I'm going to get really, really close to 3. So if I think of this in terms of a limit, if I take the limit as n goes to infinity of 3 minus 1 over 2 to the n, clearly this goes to 0 in the limit, so this is actually equal to 3. If I keep going with a5, a6, a7, I should very quickly convince myself that this is getting closer and closer to 3. Therefore, in this case, an converges to 3. Now let's take a look at this one. I'm going to use this idea of the limit again. I'm going to take the limit as n goes to infinity of n over negative 3n plus 1. Now that goes to infinity over infinity, which is an indeterminate form. And so we can actually use L'Hopital's rule on this. Now, you know L'Hopital's rule is applied to continuous functions. This is definitely not continuous. But we're going to formalize this idea a little bit later. For right now, we will use L'Hopital's, and it's okay. And like I said, I'll formalize the idea a little bit later and kind of show you why this truly works. This is just really kind of an overview. So by L'Hopital's rule, this is equal to the limit as n goes to infinity of the derivative of n dn will be 1 over the derivative of negative 3n plus 1 dn will be negative 3. So this goes to 1 over negative 3, or a negative 1/3. Therefore, an converges to a negative 1/3. This next example, I'll do the exact same sort of thing with. Take a look at the limit as n goes to infinity of 1 over n. That definitely goes to 0. Therefore, an converges to 0.